All right, so let's take a look at how I decide to do this. Like I said, you set up a second vertice called u and set it equal to -1. In other words, it's not set to any actual vertex in the graph at first. So for every single element in the upper triangular portion of the adjacency matrix, since we're representing this as an adjacency matrix, we check if there's an edge between those two vertices, between vertices I and j. And if there is, then we check if the assignment for I and j is 0. That is, they're not none anymore. We have specifically set them to not be in the assignment. Well, if both of them are explicitly out of the assignment, and there's an edge between them, well, then that's not going to be a valid vertex cover. So we return float infinity. Now, otherwise, if we find that the assignment for both I and j is equal to none, then that means we haven't actually looked at this yet. So it's a good candidate for setting v and u. So then we set u equal to I and v equal to j. And we continue on. Now, once we go through the entire double for loop, we check if v is still unset. Because if v is still unset, that means that, first of all, we didn't fall out of this by not having a valid vertex cover. And second of all, it means that all of the vertices have been assigned to something or other. Because that's the only way that v could still be set to -1. And if v is set to -1, then note that u also is. Now, if that's the case, then we set a variable size equal to 0, and we start simply counting up all of the different vertices in the assignment. If the vertex is set in the assignment, then we increment size. If it's still unset, well, then we have to do a little bit of manipulation here. We have to set the vertex I to 1 if a neighbor is 0, because we want to make sure that this is still a valid vertex cover. So for every j in range I, I just realized a bit of an error here. Well, not an error necessarily, just a slight inefficiency. We can boost this to I plus 1, since we don't allow any loops in the graph. If we did, then we would have to simply use I. But this doesn't really particularly matter for this. Moving on. So for every other vertex in the graph, we check if there is an edge between I and j again. And if there is, and if the assignment of j is 0, well, then we have to set I. And we say that the size is an additional element because we've now had to set I. And once we go through all this, we return the size, and that's done. Now, for each of these, for the recursive part that you didn't have to worry about, we try all of the different possible combinations that aren't 0, 0, since that would not be a valid vertex cover. We try 1, 0, 0, 1, and 1, 1. We compute the size for each of these, and then we return the minimum of those, and compute this whole thing recursively. So that was a little tricky. If you had trouble with that, totally understandable. This does give you a little bit of a improvement in the total size of the search tree we end up searching through. Before it was 2 to the n. Now we've got about 1.733 to the n. That might not seem like much, but in practice it can be helpful. So, okay, let's go ahead and look at a different problem now.